Okay, let's move on to isomers and conformations. And for this section, and really the remainder of the class, but especially for this section, it might be helpful to have handheld models, so a model kit. It's not necessary, it's not required, I guess, but a model kit might come in handy for some students in this section. Okay, so first of all, what is isomerism? And isomerism is defined as a property in which two or more compounds have the same molecular formula, but different arrangements of atoms. And we're going to take a look at some examples. And one of the I think the first example we'll take a look at is if you have the molecular formula C2H6O. Okay, and I'm not going to answer this right now, but if we have this molecular formula, two carbons, six hydrogens, and one oxygen. It turns out there's two different ways that you can put these atoms together to build a molecule. Okay, so only two different ways you can do that. And when we have these two different compounds that are made up of the exact same atoms, but they're ranged differently, we call those isomers of each other. And to give more detail on that, a structural isomer, well, structural isomers are compounds that have the same molecular formula, but in which the atoms are bound in different patterns. So we have different bonding patterns. The number of possible structural isomers increases dramatically with the number of carbon atoms in an alkane. So if you remember an alkane, okay, an alkane only consists of carbon and hydrogen, so it's going to have some formula. It's usually CnH2n plus 2. And you can see here that if you have C4H10, that follows the formula CnH2n plus 2, right? 2 times 4 is 8 plus 2 is 10. And there's two possible ways that you can arrange four carbons in 10 hydrogens to make unique molecules. If you move up to 5 carbons, so again, see this follows the formula CnH2n plus 2. 2 times 5 is 10 plus 2 is 12. There's three different ways, but you can see how it increases dramatically once you get up to 10 carbons. So 10 times 2 is 20 plus 2 is 22. We have 75 different isomers, and then it really just goes off the rails here. You get up to 30 carbons, you can have over 4 million different isomers. Now, there's no formula to predict how many possible isomers, but the point is that the more carbons and hydrogens we have, of course, the more structural isomers are possible. And something that you're going to hear me refer to in this class is going to be a straight chain alkane, and you'll also hear me refer to branched alkanes. Now, a straight chain alkane is going to be any alkane in which all the carbon atoms are aligned in a continuous chain. Okay, so it's just a chain linking all these carbons together. Whereas a branched alkane, on the other hand, is an alkane in which at least one carbon atom is not a part of the continuous chain. And so if you take a look at these two examples that are shown here, it says isobutane is a branched alkane, while N-butane is a straight chain alkane. And this N prefix here, this actually comes from the word normal. So it actually comes from normal. So if we have an N-alkane, it's a straight chain alkane. It stands for normal. So normal butane is just a straight chain like this. Now let's take a close look at these, okay? Both of these compounds are isomers of each other because they both have the same molecular formula, C4H10. But you see that in the straight chain alkane, that all the carbon atoms are bound together, carbon, 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 like this in one chain. Now, this is a condensed structure in this red oval here, and I don't feel like drawing the complete Lewis structure, but you could. So we have a CH3. Remember, there we go, to give each carbon 4 bonds. So we'll keep going like this. I'm drawing it a little smaller here. So, but anyhow, there you go. That's our full Lewis structure, right? This is our full Lewis structure. This is our condensed structure, condensed. And then this is our bond line structure, bond line structure, or sometimes it's called a skeletal structure. The bond line structure or the skeletal structure is actually the industry standard in drawing organic molecules. So let me just get rid of this Lewis structure and I'll give you some more background on drawing a bond line structure. So you notice that butane has the 4 carbons in a chain. So when you draw a bond line structure, when your pen touches the paper, or the screen, okay, that red dot that I made, that will be my first carbon. So I'm going to count 1, 2, 3, 4, okay, and I draw them in that zigzag pattern that you see here. Okay, and so what's implied is that at each end of the line, there is a carbon, and at each angle, there's also a carbon. Now we know that carbon always has 4 bonds, and so we're going to have to fill out all these carbons, right? This carbon only has 1 bond, so it's going to need 3 hydrogens. This one's going to need 2, this one's going to need 2, and this one's going to need 3, like that. And so that is how we draw our bond line structure. Now, students will sometimes say, well, do you have to go down first and then up? No, it doesn't matter at all. If I was to, this is going to be the same thing as if I started here. 1, 2, 3, 4. This molecule and this molecule are both N-butane. They're identical to each other. Okay, so that is how we draw a bond line structure. Now, if we look at the other isomer of butane with the same molecular formula, C4H10, we see that if we look at our bond line structure, and you can see the structure shown in the red circle, you can see that we have carbon, carbon, carbon like this, okay? But, right, this carbon only has 1 bond, so it's going to need 3 hydrogens. This one needs 3 hydrogens. But this carbon has 3 bonds, therefore it only has 1 hydrogen attached to it. And so the branch that's coming off here is going to have 3 hydrogens like that, okay? So that is going to be our molecule of isobutane. All right, I'm going to erase all these carbons and hydrogens so we can see it more clearly. And again, you should be able to draw a condensed structure or a bond line or skeletal structure like is shown here on this slide. And so let's address that question that I brought up earlier on in this video. Draw two structural isomers with the molecular formula C2H6O, showing all covalent bonds. Identify the functional groups within each isomer. So if we have the molecular formula C2H6O, well, there's two possibilities, okay? Now remember, carbon can bond to another carbon. But remember that carbon also only ever has or always has 4 bonds, and hydrogen only ever has 1 bond, no exceptions. Okay? Hydrogen can only form 1 bond, and there's no exception to that rule. So that tells us that we're going to have the oxygen like this. Otherwise, there's no way that all the hydrogens could have 1 bond. So now we have to fill out these carbons. So we have 1, 2, 3 on this guy. And then ask yourself, how many hydrogens are necessary on this carbon? Well, it's got 2 bonds. So then it's going to need, oops, it's going to need 2 hydrogens. Okay, and remember, oxygen always forms 2 bonds and has 2 lone pairs. So that molecule is actually ethanol, and this is the alcohol found in alcoholic beverages. And of course, it has an alcohol in it. So this is an alcohol. Okay, and then the other possibility is to have a carbon linked to the oxygen and then the other carbon on the other side. And then we can use up our 1, 2, 3 hydrogens here and then 4, 5, 6 over here. Okay, oops, maybe I can do that better. There we go. And so now, what functional group do we have in this molecule? Well, we have carbon, oxygen, carbon like this. And so what's the functional group that we see here? That's right, it's an ether. Okay, and so this molecule is called dimethyl ether. So dimethyl ether, which is used as the propellant in a spray can, whether it's Pam cooking spray or spray paint or hairspray, any kind of aerosol can uses dimethyl ether as the propellant. And so that tells you that dimethyl ether is a gas. It's a gas at room temperature, whereas ethanol, the alcohol in alcoholic beverages, is a liquid at room temperature. Anyhow, so these two compounds, same molecular formula, but the atoms are connected together differently, and so they would be isomers of each other. Now here are some ball and stick models of the two compounds that we just drew in the last problem. So we have the ethanol here. I'll just draw it. Okay. Try to make it match a little bit of what's in the ball and stick model here. Okay. And then we have the dimethyl ether here. So CH3. Then we have our oxygen and then CH3 like this. And the point that they want to make on this slide, and I already addressed this a little bit. I said that the ethanol was a liquid at room temperature and the dimethyl ether was a gas at room temperature. But the point is, even though two molecules have the same molecular formula, their properties can be quite different, especially when they have different functional groups. So again, ethyl alcohol or ethanol has a boiling point of 78 degrees Celsius. So again, it's a liquid at room temperature, and dimethyl ether, same elements, but they're connected together in a different way. And so it has a much lower boiling point. So it's a gas at room temperature. And you can imagine the reason why this is, right? If we have an alcohol, right, we have what? We can have hydrogen bonding, which is a much stronger intermolecular force than the one in dimethyl ether. Now, it looks like the dimethyl ether might be linear the way I've drawn it here, but in fact, it isn't. Or you should know that the molecular geometry around the oxygen is bent. And so if I just draw it in here properly, I'm going to need to erase these lone pairs. There we go. It's bent like this. Okay. That means there's a dipole going this way and this way. So that means the net dipole is going in this direction. So dimethyl ether is a polar compound, but you know that a dipole-dipole force, so dipole, is not as strong as a hydrogen bond. Now, conformations of alkanes, this is where a model kit might be helpful for you. It says here the planar representations of organic molecules make no attempt to accurately portray correct bond angles or molecular geometries, right? When you draw methane like this, okay, it tells you nothing about the three-dimensional shape of the molecule. And you guys know now that it's actually a tetrahedron, right? Or a tetrahedral molecular geometry, which we kind of show using the dashes and the wedges. A model would be even better. But conformations are different arrangements of atoms in the three-dimensional space that are achieved by the rotation around single bonds. And so the molecule that's shown here, this is just it says here rotation occurs readily around butane. So this is butane. You have CH3, CH2, CH2, CH3, CH3, CH2, CH2, CH3. Okay. So if you make a model of butane, okay, what you're going to see, so if I just use a ball and stick, or sorry, a bond line structure, what you're going to see is that you can rotate this bond here, and that's what they're doing here essentially. They're making it look like they're just rotating here, but really, in reality, I think it's more accurately described as rotating this bond. But neither here nor there, you see that you can rotate this bond, and I'll highlight it in green. You can rotate this bond, which is the same as this one, which is the same as this one, so that the two methyl groups, right, the two methyl groups are on opposite sides, or you could rotate it such that, let me get my pen here, so that they are on the same side like this. Okay, maybe I'll use this pen. Okay, so now they're on the same side like this. So again, this is the green bond here, and these are the two methyl groups. Okay, and so technically there's really an infinite number of conformations because you could just keep rotating the bond ever so slightly, but these are what we call conformations, when we can rotate around a bond and have a different arrangement of the atoms in three-dimensional space. Now, if you really, really wanted to do a deep dive on this, and this is way beyond the scope of our class, okay, you don't have to know this. But these two conformations actually have names, the ones that are shown here. If you want to do a Google search on it or something, you could. But this one here is called a staggered conformation. Staggered conformation. And this one here, where the two methyl groups are next to each other like this, they're close to each other. This is called an eclipsed conformation. Eclipsed conformation. And you can draw something called a Newman projection, which helps you even rationalize it more. But again, that's going beyond the scope of our class. But in case you're interested, you could take a look at it if you want to. So, like I said, if you have a molecule or a sample of butane, I said technically there's an infinite number of conformations that are present at any instant, right? Because you have free rotation around this bond here, the bond in the middle. And so these different conformations do not represent different structural isomers. It's still the same compound, it just different rotations around that bond, so different conformations. Now it says here two possible conformations are shown here, but again, I told you that technically there's countless or an infinite number of possible conformations. But anyhow, again, this is a ball and stick diagram, but this would be the staggered conformation. And again, I'm never going to ask you about staggered and eclipsed, but this would be the eclipsed, if I can write the letter E. There we go. Eclipsed, eclipsed conformation. But again, you don't need to know the words staggered and eclipsed for this class. All right, let's take a look at a problem that you should be able to do in this class. It says, which of the following pairs of compounds are structural isomers, which are completely different conformations of the same molecule? Well, they kind of broke it down here into two sections. So there's the two molecules on the top, okay, and then there's the two molecules on the bottom. So the two molecules on the top, you can see that both are C4H10. So C4H10. And the question is, are these two molecules structural isomers, or are they just different conformations of the same molecule? Well, you can clearly see that it's the same molecule because they have the same bonding pattern, right? We have CH3 attached to a CH2, attached to a CH2, attached to a CH3. So they are both the same molecule. In fact, they're both butane, okay? So the name of this molecule is butane. The only difference between the two is that we're showing rotation around this bond and this bond, right? They're just moving these, just rotating those bonds. And so then you end up with this structure here. And so these would be structural isomers, they're simply different. So I would say these are conformations of the same molecule. Now, if we look at the second example, so 1, 2, 3, 4, 5, 6 carbons, both of these both have the same molecular formula. If you look carefully, both are C6H, so it's 2n plus 2. So 2 times 6 is 12, plus 2 is 14. 14, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There you go, 14 hydrogens. So they both have the same molecular formula, but you can see that these are structural isomers, okay? They are not different conformations of the same molecule because it's not the same molecule. If you just start on the end here, you have CH3, okay, CH3. Then you have a CH that is attached to a CH3, right? What's attached to the other CH3 in green? It's not a CH, it's a CH2 group. And so you can clearly see that these are different. And we're going to look at nomenclature later on, but if you name these two molecules, they're different. And again, I'm getting ahead of myself, but this molecule is called 2-methylpentane, 2-methylpentane, and this molecule is called 3-methylpentane, 3-methylpentane. And we'll cover nomenclature in a later video, but this is just another way of proving that these are not the same molecule, okay? And so these would be structural isomers. Okay, let's move on to classification and naming of alkanes. And it says here that many smaller alkanes were assigned common names at the time of their discovery, and they're still predominantly used today. And so it says here, however, to help systematically name complicated compounds, the International Union of Pure and Applied Chemistry, or IUPAC system, was developed, and it can be used for all organic compounds. So you need to memorize the first 10 straight chain alkanes. Okay, everybody needs to memorize them. I did. You're gonna have to. The people who come after you will. So if we have one carbon, it's methane. If we have two, it's ethane. Three is propane. Four is butane. These are kind of the toughest ones to learn because once you get to five, they start to make a little bit more sense, right? Five is pentane. Six is hexane, right? Think a hexagon has six sides to it. Heptane. Then octane, oct, right? Nine, or oct is for eight. Then we have nonane, and then decane, right? A decade is 10 years, okay? And so here you have the molecular formulas of all of them. You can see that they all follow the generic formula CnH2n plus 2. And there are the structures of the straight chain isomers. You could practice drawing your bond line structures here. So there's no bond line structure really for methane because it only has one carbon. But for ethane, you'd have, two carbons connected like this. For propane, it would look like this. Butane is 1, 2, 3, 4. Pentane would be 1, 2, 3, 4, 5. Oops, 1, 2, 3, 4. Oh, you added an extra carbon. 1, 2, 3, 4, 5. There we go. Hexane would be 1, 2, 3, 4, 5, 6. That's better. Heptane would be 1, 2, 3, 4, 5, 6, 7, etc., etc. And so you can practice that if you want to. Now, when it comes to naming alkanes using the IUPAC or International Union of Pure and Applied Chemistry naming system, there's three parts. You're going to have the root, which describes the longest continuous carbon chain. And the way you're going to find that longest continuous carbon chain is going to be by trial and error. Okay? Students sometimes don't like that. But anyhow, that's how you find it. You just look until you find it. Then you're going to use a prefix that denotes the number and identity of different attached groups. And then the ending is going to tell you what kind of functional group is in there, whether it's an alcohol, aldehyde, carboxylic acid, etc. So we have the prefix, we have the root, and then we have the ending. But I always like to start with the root because that means, or it's because we have to start by searching for the longest continuous carbon chain. Now, when it comes to the different types of groups that can come off of the longest chain, there are many types of different atoms or groups that can be bound to the root chain. But one of the first ones you have to learn are the different alkyl groups. And an alkyl group is a group different by one hydrogen from an alkane. Alkyl groups are one of the most commonly found types of groups that are bound to the root chain. Okay, so you guys remember methane from a couple slides ago? Well, if you remove one hydrogen, then we call it methyl. So that's a methyl group. If you remember ethane, which was CH3CH3, if you remove a hydrogen, then you have what's called an ethyl group. If you take propane and remove a hydrogen from the end, we call that a propyl group. But if you remove a hydrogen from the middle, okay, if you take a hydrogen off the middle, then you get what's called an isopropyl group, like this. Then if you have butane and you remove a carbon from, or sorry, a hydrogen from the end, you get what's called a butyl group. If you take one off of one of the two middle carbons, doesn't matter, you get what's called a sec butyl. Then when we take isobutane, if we take a carbon off of the, or hydrogen off of the carbon that only has one hydrogen, then we get what's called a tert-butyl group. And if we take one off of any of the other carbons, we get what's called an isobutyl group. And so you need to know all of these alkyl groups. There's 8 of them total, right? We have the methyl, ethyl, propyl, isopropyl, butyl, sec-butyl, isobutyl, and tert-butyl. Okay, everybody needs to memorize these different alkyl groups that can come off of your root chain. Now, this table just shows some other atoms or groups that are commonly bound to your root chain, like the halogens. So if you have a halogen, like fluorine, chlorine, bromine, or iodine. We put fluoro, chloro, bromo, or iodo. And then we can also sometimes find a nitro group or an amino group. So be on the lookout for those as well. So these are different non-alkyl groups that we might see bound to our root chain. All right, let's see if we can name a an alkane, and it says this compound is far too large to have any reasonable common name. So there's no common name for this compound, but if you look for the longest chain of carbons, if we draw a line like this, okay, we have a total of 6 carbons. If we were to do something like this, 1, 2, 3, 4, 5, 6, hey, what do you know? It's still 6 carbons. And if you're like, well, what if I did this 1, 2, 3, 4, 5, 6, right, like that? It's still 6 carbons. Well, it wouldn't matter which one of these chains you picked, they'd all give you the same answer, okay? So we always go for the longest chain. I'm just going to do it horizontally like this. And so now we can see you have a total of 6 carbons, right? 1, 2, 3, 4, 5, 6. So that means this is some kind of, and you can see that we have a total of 6 carbons in this chain. So this means that this is some kind of hexane. So our root, again, if I highlight it in green like this is going to be some kind of hexane. So now what we do is we're going to look at the alkyl groups that are attached. Okay, so this one is a CH3, and this one is a CH2CH3. So you might remember this one is an ethyl group, and this one here is a methyl group. Methyl group. So the next thing we're going to do is we're going to look at these two groups where they're attached to the root chain. If I look at the methyl group and I start on the end, I have 1, 2. So that means the methyl group is attached to carbon 2, so I go 2-methyl. Now, if I was to start numbering from the other end, 1, 2, 3, that would make this a 3-ethyl. And the rule is this, is that you want to give the first substituent the lowest possible number. So in our root chain, if I number using the red numbers, my first substituent is at carbon 2. Whereas if I use the blue numbering, my first substituent is at carbon 3. Well, what's a lower number, 2 or 3? The answer is 2. And so it's not going to be a 3-ethyl, and we're not going to use the blue numbering. We're going to erase that. We're going to continue numbering with the red number. So 1, 2, 3, 4, 5, 6. So that means I have a 2-methyl and a 4-ethyl. Now, lastly, when we assemble everything, we're going to put it in alphabetical order, our two substituents off of the root chain. And if we look at methyl and ethyl, well, E comes before M in the alphabet, and we're going to list our substituents in alphabetical order. So the name of this compound is going to be 4-ethyl 2-methyl hexane. All right, now, you probably noticed that when I separated numbers and letters, I used a dash, and we always do that for numbers and letters. If we have numbers and numbers, we use commas, but if we have a number and a letter, we always use a dash to separate them. We don't use any separation between the two letters here, methyl and hexane, that makes one big word, but that would be the name of this compound. All right, let's try another one. It says here, give the correct IUPAC name for the following alkane. So the first thing we do is we find the longest continuous chain of carbons, and in this case, it's these 8 carbons here, okay? Now you can see we've got two substituents and they're identical. CH2, CH3, that's an ethyl group. And then we have the same thing here, CH2, CH3, that is also an ethyl group. There we go. Now, which end are we going to start numbering from? Should I start numbering from this end? Or should I start numbering from this end? Well, remember the rule was we want to give the first substituent the lowest possible number. So I should start from the end with the red writing on it because then my first substituent is going to be on the third carbon. If I started on this end, which would be wrong, it would be 1, 2, 3, 4. My first substituent would be at carbon 4. What's a lower number, 3 or 4? The answer is 3. And so we're going to erase all this mumbo jumbo here, and we'll finish this up. So 1, 2, 3, 4, 5, 6, 7, 8. So if it's got 8 carbons, this is some kind of octane. And so the name of this compound, we've got two ethyl groups. There's one at carbon 3 and there's one at carbon 5. So we're going to put 3, 5. We separate numbers by a comma. We separate numbers and letters by a dash. Now, if there's 2 of something, we use the prefix di. If there's 3 of something, we use the prefix tri. If there's 4 of something, we use the prefix tetra. If there's 5 of something, we use the prefix penta. And if there's 6 of something, we use the prefix hexa. So since the two ethyls are identical, we don't say 3-ethyl, 5-ethyl octane. We say 3,5-diethyl octane. Now, there's another question in these slides that says, can you draw the structure of 3-ethyl 2-methylhexane? So the way you would do that is you would start out by drawing the root first. So I'd say CH3, CH2, CH2, right? Hexane has 6 carbons, so we'll keep going. And there we go. So that would be hexane. And then on carbon 2, I want a methyl group. And on carbon 3, I want an ethyl group. And so on carbon 2, so I would put in my methyl group like that, okay? And then on carbon 3, I would put in my ethyl group. There we go. So I'd put in my ethyl group here, which is a CH2, CH3, and there you go. We have the structure of 3-ethyl 2-methylhexane. Remember, the ethyl comes first because it starts with the letter E, and methyl starts with the letter M. So we alphabetize, right, going from A to Z.